Okay, today's plan is to finish the determination of principal axis of inertia with example 34, and I will start talking about the last topic in dynamics, which is the three-dimensional equations of motion. Not exactly the last topic. After that, if we still have some time, which I think we do, I will start talking about the vibration of single degree of freedom systems. And that is the bridge topic to the graduate level structural dynamics. Result on my notes, page 62. You know, we have been trying to determine mass moments of inertia and mass products of inertia. Why are we doing that? Is because in general, any object, if we don't know, or if we cannot determine its principal axis of inertia, if we just don't know, and you have this three-dimensional object defined in a three-dimensional space, which means you cannot really see what's the principal axis. You cannot find the axis of symmetry. In that case, can we still define the three-dimensional coordinate system at the center of gravity? Suppose you know the center of gravity, you just don't know that whether they are symmetrical or not. Suppose it's here. If you have an object which you cannot tell what is the obvious axis of symmetry, but you can still define the x, y, z, right? According to what? According to the local coordinate system. So you have this object in the three-dimensional coordinate system. This is our space, x, y, z. You can certainly define the x, y, z of this object. Also, they are not necessarily the principal axis of inertia. Of course, right? You just choose a coordinate system, define the x, y, z here. Of course, this arbitrary selection doesn't necessarily give you the principal axis of symmetry. However, if we can define the x, y, z of this object in arbitrary shape, then you can calculate the mass moments of inertia of ix, x, iy, y, and izz. And you can also calculate mass products of inertia, ixy, iyz, and izx, correct? So the calculation of all these, what we call inertia tensor, I'm just going to call this one here. We call it inertia tensor, which contains 6 quantities, 3 mass moments of inertia and 3 mass products of inertia. This selection of x, y, z can be written as this, which, okay, so let's write it like this, iyy and izz. And this part is symmetric. Because x, y, z are not principal axis of inertia. So your inertia tensor is going to be fully occupied. However, one could imagine that if I rotate the axis to certain angles, suppose I rotate the x-axis by this angle alpha, and the y-axis by angle beta, and the z-axis by angle gamma. Like this. If I do that, and I can identify or move this axis to their corresponding principal axis of inertia, which of course in theory, and also in practice, this can be done. Because you choose an arbitrary reference coordinate system, you just have to rotate it to a certain angle, and that angle will be at the principal axis of inertia. So let's say that we don't know this angle. We don't know alpha, beta, and gamma, but we know that the angular relations between an arbitrary selected alpha x, y, z and the principal axis, which you can call them x prime, y prime, and z prime. They are actually measured by this angular difference, which is alpha, beta, and gamma. And if we do that, then the inertial tensor can actually be simplified into just this, which is I x prime, I y prime, and I z prime. And all the off-diagonal components will become 0. 0, 0, 0, 0, 0, 0. So this is the difference and the value for finding the principal axis of inertia. Because if you do not know what the principal axis of inertia are, you will have to deal with 6 quantities, which is here. But if you know the principal axis of inertia, you just need 3 quantities. Which one is nicer? Of course, this one. That's much easier. So today, I'm going to show you how we can determine these. How do we convert an arbitrarily selected coordinate system, x, y, z, to x prime, y prime, z prime? So that's the purpose today. For example 34. To save our time, I would choose a two-dimensional object. And this is just to, for the convenience of our discussion. You can certainly use this technique and apply it to 3-dimensional objects. We choose 2 just because it's easier to do the math. And here, suppose you're provided with a tensor, an inertial tensor. I, and this I, of course, is not this inertial tensor is not measured with respect to the principal axis of inertia. So it's just with respect to x, y, z, which is arbitrarily selected. And as a result, I will just give you the value here. Of course, they are random values. Just suppose you can find an object that you can calculate the mass moment of inertia, then this will be the mass moment of inertia with respect to the x-axis, and this will be the mass moment of inertia with respect to the y-axis, and this will be product of inertia with respect to xy plane, and this will be the mass product of inertia with respect to plane yx. Okay, so this is just like the example that we did before. And if that's the case, we want to know what? We want to know that find this angle, alpha and beta. Because we are dealing with 2-dimensional object. This is a 2x2 matrix. Of course, it's on the 2-dimensional domain. So we want to find angles, alpha and beta. And this way means we can determine, actually, let's find first, let's find x prime and ix prime and iy prime. That means the principal mass moment of inertia. So this is what we want to do. Now, how do we solve this problem? First, to solve this problem, you have to use a technique, what we call eigenvalue analysis. So what is eigenvalue analysis? Eigenvalue analysis means this. We have this I, the inertial tensor. And if you minus this, subtract a matrix from this inertial tensor. And we're going to call this thing is called lambda times a identity matrix. So identity matrix is called one. It's also a matrix.